Okay, in this video we will be continuing with the oscillation topics. Firstly, we will be talking about the motion of a loaded spring. Now consider a spring whose length is L, and if that spring is stretched by a weight. Okay, this we suppose, let us take a metal box or a metal which is having a certain weight, and it is pulling the string downwards, and let the string extend through L. Okay, small letter L. The original length is L, and the weight of the metal will be, or the object will be, mg, right? Mass into gravity. And the restoring force, according to Hooke's law we have studied before. According to Hooke's law, the extension produced in a wire is directly proportional to the load, right? That is Hooke's law. It means that the extension, this L, the extension produced in the wire is directly proportional to the amount of force, mg, right? So the restoring force is in this direction. The weight is in the downward direction, but the force is in the upward direction. So it means that the weight is pulling the string downwards, but if we let go of it, suddenly the force will be pulled in the upward direction, right? The string will bounce back, so they are opposite in direction. So according to Hooke's law, force is directly proportional, the restoring force is directly proportional to the extension produced, right? The amount of length produced. Or if we write it equal to sign, we will put a constant term K, spring, which is called spring constant, right? But since they are, like I said, since they are in opposite direction to each other, we will put negative sign, and this K is called a spring constant. Now if this length, the extension produced length, this L, if it is 1 unit, right? It means that if it is 1 meter or 1 centimeter or 1 millimeter or whatever, if its value is 1, if this L is 1, then F will be equal to K. Okay, I will not put negative sign because negative sign just simply shows the direction of the force. So negative is not always important. It's not always necessary to be put in the formula. So if the extension, if the string is lengthened, if is elongating by unit number, means 1 meter or 1 centimeter or 1 millimeter, if its value is increased by 1, then this L, if it is 1, then F force will be equal to K. So the spring constant can be defined as the restoring force set up per unit extension in the spring. Okay, if the extension is of unit length, then the spring constant is equal to the restoring force. Okay, so that is just for extra knowledge, okay, extra understanding. Now, what is this force actually? The force applied by this object, the force will be its weight, right? Amari nakha awire nakha a force pek chuni mai chowang chuan, the force will actually, the force applied by this object is its weight only, right? So F is, and for this F is equal to minus KL, let's give this equation 1, and the force given by the object to the string will be equal to its weight, right? So the force is mg, but actually it is, like I said, is in opposite direction to the force, so it is negative sign. Now let's give this equation number 2. Now from the equations 1 and 2, what do we have? From equations 1 and 2, they are both force, right? So m minus mg will be equal to minus KL. If we compare equation 1 and 2, and if we cancel this again, it will be mg is equal to KL. Okay, now let me rearrange this. Okay, let me rearrange this. If I put K under M, so under L, G will be there. Also I cross multiply it. Okay, I just rearrange it. Now let's give this equation 3. Now if the string is further stretch, okay, further stretch, here it is already stretched to L, and if it is further stretched to Y, okay, if it is further stretched to Y, if somebody is pulling this string, okay, tumoni khan he low po belt ta se he ay thuya Y L la input fan to sakha Y thing low po belt ta se noi lam panga hian, then there will be a new force, right? So there will be new restoring force, so that let's represent it by F dash, okay? So just like this equation, the new force for this third case, okay, before the original length is up to point B, and then when we apply an object, it is stretched up to C, and if we apply another force, then it is elongating up to point D, let's say, okay? So the new force will be, just like this formula, it will be minus K L plus Y, right? Because it is increased by L and Y. So for the third case, it will be L plus Y. Now let's give this equation for, if we subtract equation 4 and equation 1, okay, if we subtract equation 4 and equation 1, what will we have? F dash minus F minus F will be equal to minus K into L plus Y minus KL, right? If I subtract the right hand side and the left hand side, so minus KL plus into minus KY, minus into minus will be plus KL. Here this and this will cancel, so F dash minus F is equal to minus KY, okay? Now let's give this equation 5. So I just subtract equation 1 and equation 4. Now from Newton's law of acceleration, from Newton's second law of motion, what do we have? Force equal to ma, right? This we have studied in other units. F equals to ma, this is very famous. Now just like that, this force F dash minus F will be equal to mass into acceleration, right? Where m is the mass of the object, and what is the acceleration here? Enge ay khoi lai chunga acceleration lai chu intimate theta he heta input fan hi ti chat ta thut tai la a string kha te nain ain volet don ta te ro chho zong in khami avo a chho zong chak zong a kha speed kha khami kha acceleration lai chu ni don ta. Then what will be a will be equals to F dash by minus F by m, right? So what is F dash minus F? F dash minus F is minus KY, right, from equation 5. So minus KY by M. Now if we look at the previous video, okay, this is the third video for oscillation, and if you look at the second video, the part 2 of this oscillation, we have already derived the time period of simple harmonic motion. Time period of simple harmonic motion is given by 2 pi root y by a. Video masazoka in n1 2 pi root y by a ti time period of simple harmonic motion he can derive to nita. So we will use this one. We will use this equation for this one, okay, minus ky by m. A equals to minus ky by m. A equals to minus ky by m. So for a, I will put minus ky by m. So t is equal to 2 pi root y by minus ky by m. So over here, and I will not put negative sign anymore, okay? Negative kha chon in a direction na anti vel kot khan ita chuan chuan itai chon negative ikan da tel vek her zel lawanga. Since it is showing only the direction, we will not put negative sign anymore, okay? So y and y will cancel. So what will we have? 2 pi root m by k, okay? This m will go upwards. And if we look at this equation 3, what is m by k? M by k is L by G, right? So I will substitute it again. 2 pi root L by G. Okay, if using equation 3. So this is the required equation. Okay, the time period of a loaded spring. This is actually the same as the time taken by a pendulum. Okay, pendulum hetia in thena hetilai point atanga hetilai point athen thagna na a time taken equation men khale 2 pi root L by G chu chapter danglam danga unit danga gan soi to a. For it is the same case. This is equal to the time period of a pendulum, and it is the same case for motion of a loaded spring. Okay, so if we stretch a spring by any mass or any weight, and if we release it, the string will be bouncing back with a restoring force with and certain acceleration, and the time taken by that spring to bounce back to its original position, depending upon the weight of the object, can be calculated by 2 pi root L by G, where L is the extension produced in the string, okay, and G is the acceleration due to gravity. Now we'll go to the next topic, which is a simple pendulum. Simple pendulum. Now we will derive the equation to calculate the time taken by a simple pendulum. I hope you know what is a pendulum, right? So a pendulum, here it is fixed, right? And if a string is attached to it, and this is called the mean position. Okay, ain khai me lai kha achet lo lai kha, that is the mean position. And this point where the string is fixed, this point is called point of suspension. Okay, this point is called the point of suspension, and the maximum distance where it can swing, okay, up the extreme point, the maximum point where it can swing is called, this length is called, this point is called, no, sorry, then the pendulum, the center of the pendulum, okay, the center of the pendulum is called the point of oscillation. Okay, the center of the pendulum is called the point of oscillation, and the distance between the point of oscillation and the point of suspension means the length of the spring. Okay, that is what we call length of pendulum. Okay, length of pendulum, the distance between the point of suspension and the point of oscillation is called the length of the pendulum. That is just for the introductory part. Okay, now consider a pendulum moving. Consider a pendulum having a thread, a very thin thread whose length is L, and let it reach its maximum value, maximum length. Let the maximum displacement be Y. Okay, let the maximum displacement be Y. So let the angle, and at that point, let the angle made by it, let it be theta. Okay, now how will we calculate the value of theta? How will we know the value of theta? Suppose we draw an imaginary circle. Okay, if you take your compass and if you put the needle over here, and this L, if you take it as radius, then you can draw a circle, right? So what does that mean? It means that this L will be the radius, right? L will be the radius. So in a circle, remember that the radius, if we draw any true radius and the measurement of the angle between that true radius, how will we know it? We can know it by dividing the value of the radius and the value of the arc. Okay, so this is L, right? This is L, and this is Y, right? So if we divide Y by L, then we can know the value of the angle between the two radius. Okay, so from that we can know theta is equal to Y by L firstly. Okay, now we will resolve this pendulum in two components. Okay, the direction of this bob, okay, metal bob is a bolt here, a bob kante here. We will resolve it into two components. So firstly, the force will be acting in vertically downward direction, right? Mass into gravity. The weight of the bob will be acting vertically in downward direction. But since it is going in here, also we can draw a circle around a pendulum, right? It is moving in circular motion. So just like our previous video, we will resolve it into two components. Okay, we will resolve it into two components. One is in this direction and another is in this direction. Okay, so in this direction it will be mg cos theta. Okay, mg cos theta, and the other opposite direction will be mg sin theta. So, and here is this vertically downward direction mg. Now first let's talk about mg sin theta. Okay, so what is the force? What is the force in this direction? The force is mass into gravity, right? So the force of the force given by this bob is the mass into gravity, but if we are going to take it along this direction, then force will be mg sin theta, right? But actually the pendulum will be moving in this direction, right? But mg sin theta is along this direction. If you look at my arrow sign, so it will be in opposite direction. So this component is in opposite direction of the motion of the bob, so this will be negative. Okay, minus mg sin theta. It negative sign shows that, indicates that the restoring force of the bob, the restoring force, the force on the bob is in the is in the opposite direction of the angular displacement. Okay, now from Newton's second law of motion, again, what do we have? Like the one we used earlier, acceleration is equal to F by m, right? From Newton's second law of motion. So if we substitute this one, A equals to, what is F? F is minus mg sin theta. So minus mg sin theta by m. So here m and m can cancel, so A will be equals to minus g sin theta. Now this value of theta will not be that big. Okay, this value of theta will not be a very big one. Chang pei chon hemi pendulum in 10 thei thui zong hi centimeter thum lek te centimeter nga lek te ni thin. Chuman chon hemi hi kak zau tak kha ni don lo ta. Chuman chon helai in kar theta hi degree tam tak kha ni don lo shim ta ni. The value of since theta, the pendulum can swing even up to, sometimes it swings up to 3 or 5 centimeter only. So this value of theta will not be very big. So it does not make a difference whether we take it as sin theta. Okay, theta hit atam don chuan lo wangin sin theta anga zukla kher po khu angai chuang lawa an neglect don ta ni. Since theta is not big, then sin theta will be nearly equal to theta itself. Okay, so we will not write it as sin theta, so we can write it as minus g theta. Okay, now if we look at this, our first equation, theta is y by l, right? It is arc divided by radius, right? Arc divided by radius is theta. So for theta y by l, I will substitute it over here. Okay, A equals to minus g y by l. I will write it like that. So A is equal to acceleration is equal to minus g y by l. So if I solve this, if I cross multiply A and L, okay, if I interchange their position, then L will be equals to minus gy by A, right? And below L, if I put G, L by G will be equal to minus y by A again, right? So L by G equals to y by A. Now, like I said, negative sign just indicates the direction, so I will neglect the negative sign. Okay, it does not affect the value, it only shows the direction of the motion of the bob, so I will just neglect the negative sign. So again, from our previous video, the time taken by a time period of a simple harmonic motion, what do we have? This equal to 2 pi root y by A, right? This is what we have from our previous derivation of the previous topics. So if I substitute this y by A this above equation over here, then time taken by the simple pendulum will be 2 pi root L by G, right? L by G. So again, we are finding out, we are getting the same answer, okay, the same equation from of our previous topic. So it means that the same, even a simple pendulum, or even if it is a pendulum or a string which is stretched by a object by a weight, or a bob having weight and swinging, even for a simple pendulum or a string, the time taken by it, they are having the same equation. Okay, we can use the same equation. Now let's talk about the next topic, which is energy of a particle executing simple harmonic motion. Energy of a particle executing simple harmonic motion. Okay, so a particle having simple harmonic motion, hi kan soi eng tak hinge simple harmonic motion po hin lo la chiang lo mai theya. Simple harmonic motion kan ti chuanin thil che pon lampang external force le pon lampang atangal puina tel lawa ama ani dan turang tak natural dewa a che thian chu the simple harmonic motion ta ni pendulum te po kan soi ta a in then khanin i pendulum te po a in then khanin hetlai thleng hi in then to ta voi khat kha aron le na po helai thleng ai thui hi a in then to don lo ti na ni ta ni harmony de win ti hian i in lungwal de win ang kan choi nang de khani ta harmonic ani na chan po kha voi khat na po helai thleng chaw then to chuna voi ni na aron tlak le na han hetlai hi han thleng don to lo shim chuan han ten che motion thil che i control thei lo ani cho pon lampang atanga kan van nam lui te ni ngot lo chuan ani dan turang thlapa i universal truth an ti ang deu an danglam thei to lo tur khan ten chi kha an che dan ro po thil ngor ri te mo vibrate te khan ten chi kha i simple harmonic motion an ti choni ta ni chuanin simple harmonic motion has two kinds of energies. Okay, we are very familiar with the names potential energy and kinetic energy. Okay, so we will sum the potential energy and the kinetic energy, so that will give the total energy for simple harmonic motion. Firstly, let's talk about the potential energy. So firstly, let's talk about the potential energy. We know that this also, if you look at the previous video, the acceleration of a simple harmonic motion is given by A equal to minus omega square y. Hey video masapo kan explain to simple harmonic motion acceleration hi hemi acceleration hi acho chona chu minus omega square y, omega hi angular frequency khanita. This is what we get from as a definition of simple harmonic motion, the acceleration value. Now again, using Newton's second law of motion, F equals to ma. If we use this Newton's second law of motion, F equals to ma, if I substitute the value of A, okay, over here, then F will be equals to minus omega square y, omega square, I will put m first, okay, minus m omega square y. A hi hemi value ka han substitute ni chuta hian, then or I can shift negative sign, right? So minus F will be equals to m omega square y, still the same. Now let us take a small distance, okay? Suppose then the particle is moving in circular motion. So suppose it is moving, if it is moving from this point, okay, at this point, from this point A to a very small distance dy, let's say, okay, up to here only. From this point A up to this point A, let the small distance be dy. Then what will be the small work done? The small work done to move it from this point A to this point will be, the small work done will be, what is the work done? Work is force into distance, right? So work done will be force into distance. What is the distance? The small distance is dy, f dy, right? But in this case, let us put minus f, okay, minus f into dy. So what is minus f? What is the value of minus f? The value of minus f is m omega square y, right? So m omega square y dy. This is the small work done. Now we don't want just the work done to go to a small distance. We want the work done to go to a big distance, right? Up to this point, y, the distance traveled, the displacement. So in order to know the value of the big distance y, if we will integrate the small part, okay? That is the purpose of integration. Integration point mo na nita small part can integrate one, a total part can a big part can treat on nita ni. So if we integrate this small work done, we will get capital work done, okay? Combined work done. So if we integrate it, m omega square y dy, from what? From here, this point, let it be 0, and let up to this point, let it be y, okay? Like I said, so it will be from the limit, in the limit 0 to y. Now here, mass of the object, mass of the particle, and the angular frequency is constant term, so we will put it outside integration. So it will be 0 to y, y dy, and you may have studied in mathematics, integration of x dx is x squared by 2, okay? This is the formula. So integration of y dy will be also y squared by 2, okay? But there is still a limit, right? 0 to y, so we will put the limit over here. So again, this will be equal to, I will substitute the value of upper limit minus lower limit in place of y, okay? Upper limit minus lower limit, so it will be y square by 2 minus upper limit y, y ka substitute, y thawat tina ni maya, so lower limit 0 ka substitute, 0 square by 2. So this means nothing, right? Minus 0 square by 2 is yung manilawa. So it will be m omega square y square by 2, or we can write like half m omega square y square, okay? So this is the, so this work done can be regarded as the potential energy, okay? So half m omega square y square is the potential energy. Now let's go to kinetic energy. For kinetic energy, what, let us represent it with T, okay? In case of this simple harmonic motion, the kinetic energy is given by, T is given by half mv square, right? So again, if you look at the first video, hemi unit of hen tuna mi hiv ka video pathumna nito video hemi ma le mi a first video khan can explain to velocity of a particle moving in simple harmonic motion, he omega root r square minus y square t can explain to ani video masale to zo ka khan kha kan mangle don ta net khan ain lalon chhozel ta. And what is r over here? R is the maximum distance, the maximum displacement it can travel, okay? And for the case of a pendulum, r will be the maximum length, the maximum displacement where it can go from the mean position, okay, from the equilibrium position. Natanga ain ten san thei bera kha r konita. Then r is the chuchu, we call it amplitude, okay? R is called the amplitude of the simple harmonic motion. Now if we substitute again, okay, so v is equal to, if we substitute this value of v for this kinetic energy v over here, okay, so T will be equal to half m v value omega root r square y square t hetlai v again can substitute to panga, so will be omega root r square minus y square square, I don't turn it, so v square and even, so it will be half m omega square, actually here root square means it will be r square minus y square, right? So again we still have to put this inside bracket, and so this is the kinetic energy, okay? So what will be the total energy? The total energy will be potential energy plus kinetic energy, which is equal to, what is the potential energy? Half m omega square y square, so it is half m omega square y square plus And what is the kinetic energy? Kinetic energy is half m omega square r square minus y square. Half m omega square into r square minus y square. Now I will open the bracket. Half m omega square r square minus half m omega square y square. So this and this will cancel. So we have half m omega square r square. Right. So this is the energy of a particle executing simple harmonic motion. Okay. So how will we calculate the energy having simple harmonic motion? By knowing the mass of the particle, the angular frequency, and the displacement, the amplitude, the maximum distance it can travel. If we know these values, we can know the energy of the particle executing simple harmonic motion. Okay. Now there are a few very simple terms like free oscillations. These are just the definition. Okay, there is no mathematical part. Free oscillations, and there is forced oscillations, and resonance, damped oscillations. I will explain this very quickly, okay, in Mizo. Free oscillations, I will just say the definition in English. Free oscillations, when we talk about free oscillations, it is a body is said to be executing free oscillations if it vibrates with natural frequency. Okay, free oscillation, body is said to be having free oscillation if it vibrate with natural frequency. Ani dan torang tlapa na chin nakasayang deo kan ani dan torang tlapa i-vibrate ka free oscillation ani tani. Example at one, biakin darte po chokidari na vota kung atita kami ari kho ka mishingina kan vonon le char te ni lem lo chuanin kami voi khat vo ka a kho ka top toro lo ti khanom ziam don lo ta mo abdara kha kan lo han vuan ding te ni lo chuan a top hun kha ani dan tur adar quality ve shim khan ta ting gitar te po kan lo per don ta voi khat kan thai thak pop khan ari ta ni a top ngal muk lo ta kan ko ta kan dang le te ni lo chuan kan voi khat thai thak ri kha he second som te dai ta te ro second som panga te pon yang kami in vibrate a natural frequency ani dan tur ve shim ri kha free oscillations chu ni ta ni. Then what is forced oscillation? Forced oscillation, the oscillation produced by oscillator when under the effect of an external force. Okay, under the effect of an external force. So force oscillation minga tang pon ti lui ani chu gitar te po angayang po ken chu voi khat ka pera ari top thleng kan nga kha chuan free oscillation tama se ngak lawa khatia kan per charger kan zai chung khatia kan per charger ka chuan mishing an external force pon lampang atang kan low pek effect ani to khang kha chu khatiang ri kha chu chawang chung khatiang kha chu force oscillation. Tin pendulum te po hetia ama in ten top kha chu free oscillation ni ama se a in ten lai khan kutin hlei de kan ten lovati tai la lung kha khatiang kha chu ama thuwa in ten ani to lowa force oscillations ani to ta ni. Then what is resonance? The resonance, the phenomenon of setting a body into oscillations of large amplitude by an influence of another vibrating body. Vibrating body le another vibrating body anin sut khan kha resonance tunitani. When two vibrating bodies hit each other, in simple words. Okay, etinan radio te chutun ra te kan war to lawa radio te kan pi le po te nan ngai kha kan her khan ari kiuta chenom ten radio long ngai thak ve phei chuan a signal kha kal boy the chenom te radio te po man dei thei man lai hunanga kha chuan mo tu lai chun kan tam to lawa zo kan kha tiang chi kha when two vibrating bodies of high amplitude, when they strike against each other, that is simply what we call resonance. Then damped oscillations kan ti chuan damped ti khanin undamped ti den po omsang thawa undamped ti le damped oscillations ti omsanga undamped ani chuan thila in vibrate to chuanin ngai rang wave angai anga kal rengang chi kha hetia a wave angin ro don tai la hetia engma reduce po am chuang lawanga yanga vibrate heireng pon lampang atangan lo ti top ma chu vibrate hereng ang chi kha undamped zo kanita achan chu friction le khang ten chi external force omlo na ang chi friction of air mo air friction vel omlo na ang chi a thleng thei heng hi chu chuan damped oscillations taka chu thil ri a zui tel tel a frequency po tin wave po draw do ni la tia zui tel tel ang chi kha damped oscillation chu dari biakin dari ang te po ni vek thawang chu khanga khan kha hengi chu tramstate te nia derivation le han cho ngai le khan tiang kha omlem lo hengi chu a definition vel khain dok reve don ni kaman mo via wa video re yang ti ka lawa I in thre thiam lo chuan har san na in nei ani chuan I private point ta to na ka explain atanga la hre thiam lo lai heng lai number vel la equation vel bo riau na lai in nei chuan min ron zot mei don ne